Um, so yesterday I made some basically very general statements, and most of them were just words about the general structure of asymptotic symmetries in flat spacetimes and what to expect in the story that I'm telling here. But I didn't really write down any specific equations, and obviously that's always a nice thing to do. So today, I think I'll spend most of my time writing down some explicit details of the things I mentioned yesterday. First in QED, and we'll spend maybe most of the time in QED because it kind of captures almost all the interesting things that I want to talk about. And then we'll basically do the same thing quickly in GR, talk about what new things arise there, and then for super translations and super rotations and non-abelian gauge theories and all of those things. So my hope is to finish up all like these sort of soft theorems, things associated to soft theorems in all of these theories today. And then I can talk about maybe black holes and stuff tomorrow. Yes. So, okay, so as I said, maybe let me give a brief introduction to the black holes story. So, if I could, like for instance, consider an eternal black hole. So if I just draw the so if I have a Schwarzschild black hole that just looks like that, so remember I impose my matching conditions over here. So what I'm going to do today, so when I have just Minkowski space, which just looks like that, so I have my matching conditions over here, and I'll construct my charges over there, but then I'll kind of introduce boundary modes and then integrate them over all of this surface. I can basically expand it into any Cauchy surface. And then this will be a charge that acts on an in-state, out-state, and this will be a charge that acts on an out-state, on an in-state. For black holes, you no longer, this scribe plus is no longer a Cauchy surface. So even though I have matching conditions, you have to define charges on the horizon as well as on the. So the conservation law in that case will end up being looking something like QF minus is equal to QF plus plus QF on the horizon. And so then basically the idea is that there are super translations or soft modes that are also entering the horizon, which you have to keep track of to maintain this conservation law. That's really all there is to it. But then then maybe something more interesting happens if I further consider evaporating black holes. So if I consider evaporating black holes where you have a singularity for a bit and then the black hole evaporates. So the conjecture is that this conservation law continues to hold, but we have the usual issue that we have Hawking radiation and we want to preserve unitarity. So the point is that the current guess is that the unitarity is restored by correlating late time to early time radiation. But after this story, the conjecture within this story is that the Hawking radiation is correlated to the soft modes, not early or late time. So even the Hawking radiation or anything that's going in has to satisfy this conservation law, and the Hawking radiation corresponds to the hard parts of all of these things. But even if I have a hard part, you must necessarily accompany that with a certain soft radiation. And whenever I'm doing any sort of measurement which measures only the Hawking radiation, you're in essence tracing out all of the soft modes. And if you put all of those in, you recover unitarity. In essence, that's kind of what's happening with scattering amplitudes in exactly the same way. I'm only measuring energetic modes, so the S matrix is 0. It's not, you have infrared divergences. But if I include, so there was a recent paper on this which kind of briefly mentioned how if I include all of these soft modes, you can recover the unitarity of the full S matrix. Yeah.
Can you count the black hole entropy by counting some?
That would be the holy grail, but not yet. We don't know how to do that. Yes. What do you mean? But this is not a killing vector. This is an asymptotic. I mean, the asymptotic f that generates the asymptotic super translations, for instance, super translations is not a killing vector. It doesn't preserve the space-time. It takes you from one space-time to a super translated space-time, which is different. But for instance, the point is that you can distinguish. So the black hole, the no-hair theorem, which states that you only need to prescribe 4 things, mass, charge, and angular momentum, to completely describe a black hole, falls apart when you know that a black hole, in addition to mass, charge, and angular momentum, you need to also prescribe all of these infinitely many charges to completely describe a black hole. In other words, a Schwarzschild black hole and a super translated Schwarzschild black hole, even if they have the same mass, charge, and angular momentum, they'll have different these charges, and that can be measured. And there's been a proposal for what actual measurement. Andy made a proposal for the EHT. So the proposal that the EHT is supposed to take a picture of the horizon. So it seems like the Event Horizon Telescope, which is coming up. So they're supposed to take a picture of the Schwarzschild horizon if I have some particle moving, and they're supposed to see something that looks like this for a particle that's orbiting the black hole. So they're taking a picture of Sagittarius A star, which is the black hole at the center of our galaxy. And you're supposed to see the path of any particle that's moving very close to the horizon is supposed to look like this, with this line becoming increasingly small as it goes closer to the horizon. And the claim is that if the black hole is super translated in a slightly different way, then this line will have some very small wiggles that you should be able to measure. Again, they'll be tiny of order G Newton compared to what it is. I don't really know if it can be actually measured, but at the EHT. But theoretically, there's a way to measure the difference between a Schwarzschild solution and a super translated Schwarzschild solution. Maybe that shouldn't surprise you, because strictly speaking, when I'm saying Schwarzschild solution, a rotation is a diffeomorphism, but it's a large diffeomorphism. So you certainly never say that a rotated Schwarzschild solution, which is a curved solution, is the same thing as the Schwarzschild solution. They're physically different metrics, right? Even though they're associated by just a rotation, which is, after all, a diffeomorphism. The difference is that it's a large diffeomorphism. So the only thing that's being said is here, the Lorentz transformations are not the only large diffeomorphism you should care about. There are these other infinitely many large diffeomorphisms. Yes, I. Yes. Okay, so that's just the point, that there is a way to distinguish between these things because these are all large diffeomorphisms. And so in fact, there's a proposal for there's a way to say that, show how if I, also there's another way to show how to construct a super translated Schwarzschild solution if I give you just a Schwarzschild solution with no super translation. What is the exact, so you should throw in a certain, it's like a Vaidya solution where you throw in a null shock wave, but you throw in a null shock wave with a very particular angular profile, but which has the angular profile is such that the integral over the sphere of that angular profile is 0. So that doesn't change the mass, but it's going to do something else to the black hole. And you can then show that the something else is basically a super translation. That's kind of what I'm going to talk tomorrow. But that's the idea.
The point is going to be that you super translate this metric, but not our sense.
Yes. Yes.
If you super translate everything, you won't be able to.
Yes. Absolutely. Okay. Yeah, and the way to achieve that, how to super translate the black hole but not us, is to kind of throw in a Vaidya type shock wave with a certain type of angular profile, which will achieve that process. That's the physical way to do that. Okay. Okay.
And black holes in AES4 would not have any of these, would really have no head there. No matter how large the AES was.
Yeah, that's right. Yeah. Okay. So if you don't remember any of what I said yesterday, maybe the only thing that's important is that there is a matching condition. Is that for every massless field, there is a certain mode which is matched across spatial infinity in the following way. Okay, and just this very statement kind of leads to maybe all sorts of interesting things, and I think I ended with this triangle picture where there's memory on one side, asymptotic symmetries on this side, and like soft theorems on this side. I should mention, since I didn't mention yesterday, that all of this is in this review paper, this one. Okay, today I'm going to basically put in some details into this stuff here with QED. Okay, so QED, as you all know, is described by the action and like this gives the classical equations of motion. I'm just writing this down to get all my conventions straight. And this is the matter current that you get from whatever is sitting in there. So in particular, just as an example for scalars, Q is the charge. That's the covariant derivative. I've normalized things such that this Q that I write here are all integers. And the electron charge is E. That's my choice. Okay, you're probably also familiar with the usual charges that you define. To the following electric charge. Also, there's the Bianchi identity. If I don't have any magnetic charges. Oh, this is just the covariant derivative. I'm writing covariant because I'm not going to be working in the flat coordinates. Oh, that's the metric covariant derivative. D is actually, I don't have an E there, just that. Right, so these just compute for you the charges that are flowing across a Cauchy surface sigma. So you have take some Cauchy surface and then you integrate star f on the boundary of that Cauchy surface and it measures the charge flux passing through that. Okay, so QED of course has been around for hundreds of years, well 100 years, and the most important solution, the first solution that was kind of, huh? No, yes. Well, actually, almost everything. Yes, I agree. Everything I'm going to say is actually strictly speaking about classical electrodynamics. So there's like very little quantum mechanics anyway. So, right. So the first thing people wrote down was the. Okay, I don't know how to spell this. So the Leonard-Wishart or electric field, which describes the electric field and magnetic field of a moving electrically charged particle. So I'm not going to write out the full electric field, but what I am going to write down is. Right. Let me just write down the radial electric field. So ER, which is the following. So I'm just giving a very, very simple example of this antibodal matching condition, which is extremely obvious in this solution, which is known everywhere in the book. Okay, you can find this basically in Jackson. Pick up any book and any electromagnetism book and you can find the solution. And of course the radial electric magnetic field is just 0. Okay, so now I want to kind of evaluate these fields at scribe plus minus and scribe minus plus. So for that, let me first set up the right set of coordinates. So let me draw the coordinates here. So that's the Penrose diagram of Minkowski space. So I'm going to choose, when I'm studying scribe plus, I'm going to choose coordinates. I'm going to choose the retarded coordinates where r increases in this direction, u increases in that direction, and everywhere on scribe plus is a sphere, and I on this S2, so let me work in 4 dimensions. On this S2, I put in stereographic coordinates, and then z increases in that direction. On the other hand, I'll write down the metric in a minute. On the other hand, on scribe minus is best analyzed in advanced coordinates where you have r that increases in that direction, v which increases in this direction, and similarly, just like on scribe plus, you have a sphere, and you can set up stereographic coordinates on that. But I'm going to choose coordinate z, which increase in the opposite directions as the one on scribe plus. But I'm going to call them both z, even though they're different coordinates. It's going to be only slightly confusing in the beginning. Z are angular, so they're stereographic coordinates on the S2. But I'm going to use the same label z for the scribe plus coordinates and the scribe minus coordinates, but they're going to be increasing in opposite directions.
So that your identification will become then the same.
Yes, exactly. So that my antipodal identification will become f of z is equal to f of z with the same value of z. That's the reason. So just to be clear, the metric in these coordinates is so gamma zz bar is just the round metric on the sphere. Okay, and as I said, scribe plus is defined, and there's the analogous metric for scribe minus, where you just replace u with minus v. And scribe plus is defined by taking r to infinity, keeping u fixed, and scribe minus is taking r to infinity, keeping v fixed. And these are related to t, as t is u plus r, and also v minus r. Okay, so let me take those limits here. So ER, remember, in these coordinates is just FUR. It's actually, well, FRU. So let me evaluate this first on scribe plus. So for that I need to take, t to infinity, keeping t over r fixed to 1. That's the ratio. So when I do that, you can just check that you get e squared q that. And notice, in fact, that this is independent of u. This v is the velocity of the particle, not the same as that v. Notice that this is really independent of u. That's just a special property because I have just one massive charged particle. So there's no massless flux passing through scribe plus. If I had massless radiation coming through, or massless particles coming through, then this would be a function of u. So this is really a very simplistic example. So this, of course, is also the value of the field at scri plus minus. It's independent of u. Similarly, if I compute FRV at scri minus plus, let's do it at scri minus first. So that's FRV is still the electric field, the same as the electric field, radial electric field. Now I need to take t to minus infinity, r to plus infinity, keeping t over r to be minus 1. And again, a very simple calculation tells you. Right. The only main thing I want you to notice is the change in this sign. So x hat is the unit vector pointing towards a certain point on the sphere. And this is basically telling you that this, so again, now I can, because this is independent of v, the retarded coordinate, the advanced time v, I might as well just write scri minus plus. And the point is that you automatically notice that it's antipodally matched. So in this very simple example where it was a linear theory, more generally, I didn't even have to do linear Wicker. More generally, what I could do is, suppose I work in Lorentz gauge, then the solution is just written in terms of the retarded propagator. Y. And this retarded propagator, again, you can just read off from Jackson. And this satisfies the antipodal matching condition. And therefore, for any current, whatever it may be. Here I just chose a very special type of current, but here you can choose whatever, and this retarded propagator satisfies. Well, the current is conserved, only this Lorentz condition needs to be satisfied. So this G, I'm not going to write it, but you can work out what G is, translate it to these coordinates, and then take the appropriate limits, and you'll find that it satisfies this antipodal matching condition.
The equation del square phi is equal to J would also.
Del square phi equal to J would also, for this, basically, that's the same equation. Yeah. Yes. Great. So really, this is it. So for QED, you automatically. So let me maybe write another thing, which is kind of trivial in this case, but generally is not trivial. So FZZ bar, which is the transverse direction of the field strength. So it's the radial magnetic field. If I try to push that up to scri minus plus or plus minus, of course, in this case, it's just 0. Because I was considering, but if I do have magnetic charges, they wouldn't be 0, but you can check by again looking at Dirac string solutions that they're also antipodally identified. In this case, let me write it down because I'll use it later. It's just they're both 0. Okay, so that's I actually forgot r squared. Okay. So that's it. That's my matching condition. So the field, as I said, for every massless field, there's some sort of matching condition. Here, it's very clear what matching condition I should start with. It's FRU, and I need to be clear because there's an factor of r squared here. So when I take scri plus minus, you have to take r to infinity. So what I really mean is multiply by r squared and then take r to infinity. So the notation I'm going to use is if f is a bulk field, then f sub n is just equal to limit r to the n of f. So here what I mean, if I get rid of this r squared, it's just f2. And here I mean f0.
So you said this, in this particular case, it was just constant on scri class.
In this case, it was just constant, and that's because the linear Wicker potential corresponds to a massive particle, massive charge particle. If I had massless charge particle, then, for instance, if I just had a massless point charge particle, then you would have like a delta function singularity at the point where it arrives. Maybe you have other type of massless charged radiation. Okay, so in the case of QED, my matching conditions are going to be the following. FRU 2 at scri plus minus is equal to FRV 2 at scri minus plus. FZZ bar 0 is FZZ bar minus plus. And in this case, it's 0 when there are no magnetic charges. That would be F3. That is associated with the subleading soft photon theorem. That is also antipodally identified with an extra minus sign. Again, you need that by Lorentz invariance. But there's also a Ward identity associated to that, and that gives you the subleading soft theorem. Okay. Good. Okay, so we follow the process we described yesterday, and what we do is pick a function. In this case, I'll call it epsilon. I'm going to relate them to gauge transformations, so epsilon seems like a nice number. Choose any epsilon such that, which when put into the bulk satisfies this. For instance, if I were working in Lorentz gauge, you just have to solve box epsilon equal to 0 with the boundary condition that it's non-zero at the boundary, and then because that's antipodally identified, this is automatically true. And then I just define my charge. So I just say Q plus epsilon, which is the following charge, is just integral on square plus minus of epsilon F UR 2. And by all of these equalities, this is just equal to Q minus epsilon on square minus plus VR 2. I could also define my magnetic charge Q tilde plus epsilon. Now, of course, when I'm writing the magnetic charge, I could choose a different epsilon, totally independent of each other. Square plus minus epsilon F ZZ bar Q tilde minus epsilon that's not 2, that's 0. Again, in this case, these are 0. So actually, no, these are just generalizations of these things. That's what these charges are anyway, if I were to take sigma to be square plus, except with an extra factor of epsilon. This one was setting epsilon equal to 1. So already we see that if epsilon was 1, this is going to measure the total charge. And also, if you've played with gauge transformations enough, you know that the electric field integrated over with a weighting factor is the charge that generates gauge transformations. So you kind of know that already at this stage, that this charge, which I constructed purely using matching condition, is going to be the one that does gauge transformations.
So in the beginning, you didn't take it as something which was very fast.
I didn't in the way that I presented it, but the moment I write that, you just look at it, oh, this is the electric field. You just multiply by epsilon and integrate over the boundary. It generates gauge transformations. Yeah, note that it's generically 0 because, actually the correct way to say it is that the charge on sigma that generates gauge transformation looks like d epsilon wedge f. Right? This makes sense because if I commute this with a, f commutated with a is a delta function, and then it goes to 0, and then I pick out d epsilon. But then I can use integration by parts and write this as d epsilon minus epsilon df. And df is 0, so you only get something that's sitting on the boundary. So typically you consider gauge transformations that are small, which fall off at the boundary. And therefore the charge corresponding to the usual gauge transformations that you consider is 0, which is the thing that's telling us that gauge transformations are redundancy. They're not physical because they have. But here I'm specifically considering charges that are large. So this is the boundary term that survives. That's exactly that. For instance, if epsilon was 1, it would survive. This one I'm considering is already the slowest fall off that's not large. That's not small. But again, you're exactly right. I could consider things that are even larger and ask, are they symmetries? And in fact, there is one that's larger than this. It's divergent because it grows linearly with R, and it generates the subleading soft graviton theorem, the subleading soft photon theorem. You can again actually go in and ask, what if I do order R squared? And does it generate subleading? So that doesn't, for some subtlety. Well, I won't talk about that, but we can maybe discuss it later. Yeah. Okay. So the next thing I'm going to do is, so let me just now focus on this side, because this prime minus stuff is going to work out in exactly the same way. So let me just look at these two equations and massage it in a way that's going to be useful to me. So the first thing I'm going to do is I'm going to write it. I'm going to introduce a du. Oh, so note here this was square plus minus, which is just a sphere. So this just has a d to z integral. So that's d to z square root gamma epsilon. And now because I've introduced a u integral, I have this. This is not exactly equal to this. There's also a boundary term at square plus plus. But again, let's just keep it as simple as we can. Let's assume that there are no stable massive particles, only stable massless particles, and all the dynamics happens in some finite amount of time. So after event, at square plus plus, the system is in pure vacuum, and so F is just 0. So it's precisely that boundary term that contributes, that gives the extra contribution that's needed when I have massive states, and again gives you the right answer. But okay, so now I'm going to use Maxwell's equations, the equations of motion, to rewrite this in a different way. So to do that, again, all I have to do is take this equation and determine what it means determine what it is near the boundary, near square plus. So so for that I need to take, for instance, FUR, this field, and expand it in the boundary, 1 over r squared, FUR, 2 plus subleading terms. There's UA. A over here, I'm often going to say XA is ZZ bar. Just FUA is FUA 0. So these guys are function of just UXA, whereas this is the function of URXA. And then similarly J, U is expanded as 1 over r squared. So again, this is just like what BMS did. You have to convince yourself that these are the correct sort of boundary fall-offs, and this is fixed by finiteness of charge, that's fixed by finiteness of charge, this is fixed by finiteness of energy, so on and so forth. So all of these conditions can be, or yeah, again, in this theory, since it's very simple, you can really just deduce these things.
So what is that kind of stuff? Just how did that expression come about?
This just comes from that.
Integrate the third line you get.
Yeah, if I just integrate this, I get that up to a boundary term, which is 0 because I've assumed everything is in the vacuum in the far future.
So the metric UR coordinates has a UDR.
Yes, it's just that. So if I set r equal to constant, then I just have du and r squared gamma ZZ bar. The r squared here cancels with the 1 over r squared in FUR and picks out FUR2 when I take r to infinity.
So the upper metric has dr squared and du.
Yes. Oh, also, yeah, since you now mentioned, in everything I do, I'm going to raise and lower indices with gamma ZZ bar later. I haven't done any yet. That's what I'm going to be doing.
And you're going to be interpreting that as part of a Maxwell equation, so where the u and the r contract with each other?
Yes, yes, exactly.
So the bottom u component of it.
Exactly. Right, so that's what you do. You just take these fall-offs and you plug it in, and then you expand in large R and solve order by order in R. That's what BMS did for GR. I'm just going to do the same thing for QED. And the leading order constraint equation that you find is the following.
Constraint equation means bottom U index.
Yes. Yes. It's the Maxwell's equations projected onto Scribe plus. Which means the bottom U. Yes. Yes. And the it's del U FRU 2 and I feel like I notice now that I'm abusing notation. This D is the covariant derivative on S2. Let me call this curly D. So that's going to appear quite a lot because I'm writing things on the sphere. So okay, so that's just what you get. And then I just plug it. Now I have a del U. You now see the reason I wrote it as del U, so I can use this equation. Let me get rid of this. And so this charge is okay. Also, to actually get it to match with what I wrote here, I'm going to put in a 1 over e squared everywhere here, just so that epsilon equal to 1 is the. So then I get 1 over e squared du into z that's just this term. I've expanded the A index out, and I've lowered this index that cancels the gamma ZZ bar, and then this term just comes along for the ride. Yeah. Missign. That's what was wrong. Yes.
This equation, had you been doing space-like slicing, would have been del dot U equal to 2.
Yes. Yes.
And somehow you broken up the E into the RU piece and the
Yeah.
UA.
Yeah. This is what happens on a null slice. That's why being null is very important. Right. Exactly. This is going to be the soft mode, but let me just point out, since you mentioned it, on a space-like slice, this would be ftz, and that would be integral over R. But on a null slice, it's uz and still an integral over U. Okay. Oh, I forgot an epsilon. So of course an epsilon everywhere. Okay. Let me, for the moment, call this first term that I've written here Q epsilon plus S for soft. It's going to be the thing that generates a soft photon. And this thing is hard. Let me justify this terminology. So just let's think about what each of these terms would do now if I put it inside an S matrix. So remember, what's the next step? Next step is to just literally write down the Ward identity where you put this equality into an S matrix. Right. So what we did here yesterday was to just say you construct this charge QF plus S minus S QF minus into some in and out states, and the claim is that this is 0. Right. So that's what I'm going to be doing with this charge. So this first term, let's see what this term corresponds to. So this first term is linear in the gauge field. So it inserts a particle, right? But why is it soft? So let me rewrite it in a slightly more. So notice that epsilon is not a function of u. So the u integral can be pulled in, and at the end of the day, the only thing that's kind of being, this is the full u integral. And then there's some z integrals on the other side. 0. But this, is just du e to the I omega u and then this is just going to be suggestive. So what is this? FUZ is the time derivative of the gauge field, right? And then I'm Fourier transforming in the u direction, which is the time direction. So when I Fourier transform the time, you get energy. So very vaguely speaking, the gauge field, contains the creation operator or the annihilation operator, A, which creates or annihilates a particle of energy omega pointing in a certain direction x hat. I take a time derivative that pulls down omega, and then doing the Fourier transform collapses the omega integral that's sitting in there and gives you exactly this. And then you take a limit of omega goes to 0. This operator is exactly the operator that generates the leading soft. Remember, the leading soft photon theorem has a 1 over omega pole, the very important Weinberg pole, and I multiply by that omega, and then take that omega goes to 0, so it's precisely picking out the residue of the pole.
If I look at the radiation field and frequency omega,
Yes.
then this you say evaluating that field would be order.
Yes. Yes. Because of the time derivative.
Yeah.
Right? So that's already you're seeing the structure. That's why I call this soft. And this is hard because this is quadratic in the fields. So instead of inserting a particle, it's going to act on the hard states and transform it in a certain way. But actually, you even know how it acts on the hard states. What is Ju? Ju is the time component of the matter current, which is just the charge density. And you know this guy acts on a charge state and reproduces the charge. Right? It acts as a gauge transformation on your charge states.
I'm sorry, just
Yes.
an elementary question. When
Yes.
radiation field does not field symmetry, what are the non-zero components of X? Let's say I've got a field going off the straight line. Are the only non-zero components of X? All non-zero?
Generally, all are non-zero.
All are. But they dream. You want to have
But
S, Z, Z bar.
Yes, yes.
You would. Well, okay, you say that's a magnetic field, right?
That would be the radial magnetic field.
Right.
Okay, and then you also see then kind of what this dz epsilon is kind of standing for, because if I also put in the z integrals and integrate over z, that's just the polarization. So really what this, and then we'll see the reason we've chosen stereographic coordinates which are nice is because FUZ creates a positive helicity photon and z bar creates a negative helicity photon. So this entire soft factor over here is creating a positive helicity photon with polarization del z bar epsilon, and a negative helicity photon of polarization del z epsilon. And they're all soft photons because of this argument right here. Yes.
What else? Okay, very nice stuff. If I had a photon and I want to see about the relative weightage of Fij and Fij, and then I can later translate to your
You mean in R?
No.
No.
In omega.
Oh, in omega.
Okay.
Yes.
So the Bianchi identity tells me that omega times Fij should be of the same order as but they're all the same. So fine. Yeah. So they're all the same order.
Yes.
Fine. Okay, so okay.
Okay. Right. So what am I going to say next? Okay, so you kind of already see what's happening. So let me go ahead and write for you the Ward identity. And in QED, you don't even have to do that much work to just write it down. Yes,
One more thing.
no problem.
Isn't it true that radiation fields have no radial component? So the ER is 0 using normal component and normal Cartesian coordinates. Am I remembering this wrong? So the radiation field is entirely transverse to the line of sight. The electric field. Wouldn't ER be 0 at leading order 1 by 1? Or not?
No,
If I use
FRT would have a 1 over r square component because the integral of that is, by Gauss's law, is the total charge in the system. FRT is the radial electric field, and if I integrate that over a sphere, that should be the charge inside that sphere.
Right.
No,
So there's a
yes.
Coulomb field for that.
Yes.
Then I'm talking about the radiation
Oh,
part.
yeah, there's no, yes. The radiation is subleading.
Right.
Yes, that's correct.
So the non-zero components are like transfers in electric field,
Yes,
and then whatever magnetic field comes with that.
yes.
And what does that translate to in your UR course? What is the fact that there's no, that FRT was 0 at leading order in radiation? What does that correspond to here?
I don't know if it corresponds to anything. I just accept the fact that FUR is completely determined by whatever matter fields you have, and then
No, it must be the statement that FUR is equal to FRR or something. I mean, if I just take the statement FRT is equal to 0 and translate to these some equation. Just to get a sense. But
okay, yeah, okay. It's the Maxwell equation that I wrote down. It's, well, so if I remove any matter charges, if I throw away all matter charges, then FRU is just related to this. Is this what you were looking at?
Wait, I was looking for a characteristic of radiation fields that would hold true for Coulomb fields. But I'll explain.
Okay.
Just to get that. Yeah.
Okay. Okay. So let me write down the word identity. And I'm not going to bother about factors because I would ask you to trust me that they all work out also. But let me give you the generic structure of what's happening. So remember, the word identity is Q epsilon plus S minus S Q epsilon minus. And here this brackets, I mean there's an in state and a different out state over there. This is 0. This is the statement. So then, of course, the structure exactly works out in exactly the same way also for Q epsilon minus. There's a similar Maxwell equation you can work out there. Again, you can break it up into soft and hard. So if I break up these things into soft and hard, this equation reads Q epsilon plus soft minus soft is the minus sign Q epsilon hard yeah, the plus was correct, minus H, right? So this I've just expanded this in. Now the left hand side, as I've said, is just inserting a soft photon. So this charge inserts a soft photon in the future, so it's an outgoing soft photon. This guy inserts an ingoing soft photon, but an ingoing soft photon is basically equal to an outgoing soft photon by CPT invariance and crossing symmetry. So actually these two terms are exactly equal to each other. So I can map everything to just an outgoing soft photon. Could have done the opposite also. So again, I'm not going to keep track of factors, but essentially the left hand side reduces to limit omega going to 0 of omega times a omega x hat times this s. And here I want to say plus, so I'll need to give some explanation for this. What happened to the negative helicity? This one was inserting a negative helicity. This one was inserting a positive helicity. How could I collapse both of these and only write a positive helicity guy here? So this requires some explanation. I'll do that very soon. But let me just keep going on for the moment. And here, this x hat is some function of z, and I multiply this by some function, this epsilon of z, which is coming from, there's an epsilon sitting in there. and on this side, there's an integral over z. Right? That's clear, right? That's basically the structure I'm getting from this charge. So fuz, du fuz is basically the limit omega going to 0 of omega times a plus. That thing is multiplied by del z bar epsilon. You know, so this is du fuz, del z bar epsilon. I have ignored this term for a moment. I'll explain why soon. And so that's that left-hand side. The hard part, as I said, the hard part just generates a gauge transformation on your matter field. So what is my matter state? My matter state, again, let's assume everything is massless, as we have, since we've assumed everything in the far future is vacuum. A massless state is parameterized by a momentum, which has an energy, and then a certain point on the sphere. Right? So it's going to intersect Scri plus at only the singular point on the sphere. And so the gauge transformation action on that particle is just going to be a gauge transformation that acts locally at that point. So the left-hand side, I can basically write, so this is going to act on out states, this is going to act on in states, and then there's a relative minus sign. So for all particles that are outgoing, you have a gauge transformation. So what is a gauge transformation? It's q, the charge of the particle, times epsilon. Where this is this epsilon, but the gauge transformation is acting only at the point where it's intersecting Scri plus, which is this point zk, corresponding to where the direction of the momentum. And then there's a minus for all the ingoing particles, qk. And of course, the gauge transformation acts on the state, then gives you this factor times the state. So this is still left over as it is. So this is the Ward identity. Okay, so two things I have to now explain. How did I get rid of this term? And is this really the soft theorem? It looks very much like it, and it would be super surprising if it were not. So I'll tell you what the soft theorem is and why this is equal to that. There's some algebra involved there, which I don't think is illuminating. But before that, let me explain this thing. Yes.
So up to this point, everything was classical and was very clear.
Yes.
Then you made some quantum transition, which I will have to think about.
Yes.
Asymptotic. However, there's a classical calculation that classically would suggest, namely the action as a function of positive energy states at Scri plus and negative energy states at Scri.
Yes.
So, just classically you could show that what is that a purely classical statement that this thing leads to? That
Yes. Yes.
it sounds a little like this action. You would use Hamilton-Jacobi. I mean, you would use the fact that fuz is derivative of the action with respect to some creation.
Yes. Yes. Yes.
So just if I thought of a classical object, the action is function of positive frequencies here and negative frequencies there.
Yes.
And on that object, you can then show that there is a differential operator
Right. Exactly.
acting, which would be the sum.
Yes. Yeah. So I did jump to. There was a quantum jump. Quantum
jump to sounds reasonable, but it depends on what the implementation of this classical equation is in the quantum theory.
Yes.
And you have to think it through.
Yes. 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 I mean,
It's totally reasonable.
yes. Again, here just to kind of reduce the number of equations I'm writing. When I say that it's doing a gauge transformation, physically that makes sense, but you can derive it because you know what these states are in terms of, again, similarly creation annihilation modes. You know what creation annihilation modes are in terms of their respective fields. All of these fields you can push to the boundary on Scri plus, and you know how this charge. You can do the covariant phase space formalism, construct charges on Scri plus, which tells you how these act on all the fields, and then it'll give you just that.
Okay. Yeah,
Right.
but just one thing to say,
Yes.
that everything you've done, all the analysis is classical.
Yes. Yes.
The interpretation may be quantum. So it would be
Yes.
satisfying just to have a purely classical,
Yes. Absolutely.
classical algebra thing, whatever.
Correct.
Which would you do?
Yes.
This angular bracket, is it like
Oh.
efficient value in the
No, what I mean here is that is just a shorthand for there's an out state, some arbitrary out state, and an arbitrary in state.
See, this is the kind of thing you can circumvent if you just do classical calculus.
Yeah.
You don't.
Yeah, yeah.
Out state is.
So it's like it's the kind of matrix element that we are using, right? I mean, so compute the on-shell half integral is from the in particles and
Yeah.
from the out particles, and expand this graph in terms of certain number of pure nodes, and read out 5 homogeneous nodes and 7 out.
Yeah, that's the quantum statement. And classically, it is compute the action as a function of particle energy data, zero the Taylor series, and then this the soft-photon theorem is a statement of any for any amplitude. So it will be some functional equation acting on that whole
Yes.
whole action.
Yes.
So it will be some quite simple thing, which presumably uses Hamilton Jacobi here. You know,
Because it's like there is
exactly.
Right.
Del S
That
del A
makes
is equal to momentum conjugate to A, which is FU bar.
Right.
FU.
That makes sense. That has not been worked out, but that makes sense. Yes.
right. So these are just like
Okay. Any questions? Any other questions? Okay. I always find when there's too much math on a board, it gets confusing. So if you have any questions, please make sure you ask. Okay. So the reason I could basically equate these two terms is actually this second piece of charge, which I haven't used so far, and the fact that it's 0 in this particular case. So let's see how that works out. So I'm going to do exactly the same thing. Write this as del u of FUR. Sorry, this as might as well just write a few extra steps. Write this as minus sign integral over square plus epsilon del u of FZZ bar 0. And now use the Bianchi identities instead of Maxwell's equations in the exact same way. And the Bianchi identities are del u FZZ bar is del z bar fu z minus del z fu z bar 0. That's the Bianchi identity. And I basically rewrite this thing epsilon del z bar okay, and this and now the point comes, if there are no magnetic charges, then this thing is 0, which means that this is equal to that. This is telling us that in the absence of magnetic charges, you do not have independent positive and negative helicity soft photons. There's just one helicity. There's one independent degree of freedom for the soft modes because of this constraint. So in fact, this is equal to that. And so up to some factor of 2 again. So I should say approximately because I haven't kept tracks of numbers and stuff. So this is equal to that. Yes. Yes. But the moment you have magnetic charges, this is non-zero. And in that case, you'll get an extra term over there because you can still use this equation to trade this piece in terms of that, but you'll get an extra term proportional to the magnetic charges of the particle. And so you would therefore have a correction to the soft theorem if there are magnetic charges. And in fact, that's also been worked out, and it's been checked that the magnetic soft theorem is also a ward identity of these charges.
I wonder, this thing is related to what I was saying about not having an ERT component. I think
Oh,
that
I see.
If you had magnetic, if you had
I see.
the magnetic radiation would be the dual ERT field is not there.
Yes.
So that would turn on an ERT up to the level.
Yes, yes.
I think
Yes, I see. I see. Okay. Okay. Okay, so that explains this thing. So that's why I can just pick out one of them, FUZ, and it's easy to check that, because these are holomorphic coordinates, the Z generates positive velocity modes and Z bar generates negative velocity modes. Again, the details, if you really wanted to work it out, let me just at least tell you how to work it out. It's kind of simple. You just take FUZ, which has a certain mode expansion, which certainly holds for asymptotic states, right? It has a certain mode expansion. All I have to do is expand that mode expansion near Scri plus, and you have these e to the I omega x, omega p dot x sort of terms. These are very highly oscillating when r is infinity. And you'll see that because of these fast oscillations, there's a saddle point approximation and the entire integral collapses. And so the momentum space, the integral over momentum space localizes. So a field a local field at a point z creates a particle with momentum pointing towards z. This doesn't happen anywhere in the bulk because the local field doesn't create any local momentum, but it happens near Scri plus, far away because of these saddle point approximations. And so that's what you would have to do, work out the details of the saddle point approximation and see this localization actually happen. This happens only for massive fields, massless fields. It does not happen for massive fields as expected because massive fields don't reach Scri plus. They localize if I were to take the limit to time like future infinity. Okay, the last thing I need to tell you is exactly how is this related to the soft theorem. So let me massage this in a slightly different way. So this is the word identity that's true for any function epsilon. So let me choose the following epsilon. Epsilon of w is 1 over z minus w.
So this conservation law can then be written as a statement of some integral starting from the top to the bottom being 0. So it's that this is equal to this. But, but the directions are like this and like this.
Yes.
In the equality. So if I turn one around.
Yes. Yes. Yes.
And that's okay.
Okay, you just choose epsilon 1 over z minus w. And the point is, then on this side, you have a del z bar of 1 over z, which is a delta function. So this integral collapses and gives you a, you now see why I'm choosing that so that I can localize this side. Then this strictly gives me a photon that's pointing in the z direction. So then the left-hand side simply becomes limit omega goes to 0 of omega a plus omega x hat. So this is a photon with energy omega pointing towards z is equal to sum over k q k z minus zk. And now I've kind of used the convention in which I'm writing in and out particles all in one summation. If it's ingoing, then it has negative charge. If it's outgoing, it has positive charge. This still quite doesn't look like the soft theorem, which is the following statement. The soft theorem is limit omega going to 0 of omega a plus q, some momentum q, is sum over k, qk, right? That's the standard form that you're probably familiar with. This, in fact, is equal to this. All I need to tell you now, this is just a matter of algebra. All I need to tell you is exactly what is the correct parameterization of P and epsilon and Q and all of these things. And I'll just write it out for completeness. Q, remember, is to be written as something that has energy omega and points towards Z. So that's just given by omega 1. So that's just the energy. And this is the usual stereographic parameterization of points on a sphere. And this soft theorem corresponds to a positive helicity soft theorem. So I need to tell you what is epsilon plus. So here I had plus, so this is epsilon plus. And again, this is a gauge invariant equation. I can choose any gauge to describe my polarization. And it just, for the purposes of calculation, it's the simplest to work with. That's it. And pk is the same thing, with this z is replaced with zk's. Okay, so now it's just a matter of algebra. You plug all of this in there, and you just simplify it all to down to this one here. Okay, so hopefully this convinces you that the word identity is the soft theorem, and you can now see how it works out. So this is how it's going to work out in every single case.
You're going to identify the Q's as the soft term. Q plus Q.
No, q plus epsilon is the total charge. That can always be broken up into something that's linear and something that's quadratic, or not linear, maybe more complicated. The linear piece is what I'm going to call the soft charge. It's the thing that inserts a certain soft particle. And then the hard part are always going to be things that actually
Barring the fact that the sources part which gives you the hard part. So
Yeah.
Q with the S superscript is the soft charge.
yes, yes, that's the soft charge.
So can you change that soft charge throughout in the bulk by doing a gauge transformation? I know it's a nice question. By doing this large gauge transformation, can you change the value? I want to see where the bulk is this thing.
In the bulk, on a generic hypersurface, you may not have this distinction between soft and hard. So I can answer for you what happens to the full charge, but I don't know what you mean by will it change for the soft charge.
The soft charge is conveniently measured at right class.
Yes.
I'm asking, can these set of gauge transformations that allow me to define charges at right these are large gauge transformations. If I do these large gauge transformations in the bulk
Yeah.
everywhere,
Yeah.
do they change my soft charge? Because everything is defined in terms of F. I don't see them changing.
Yes, and that's associated with the fact that it's an abelian gauge group. But you would in non-abelian gauge theory. Yeah. But again, much more information is required if you want to if you want to do large gauge transformations in the bulk. The first and foremost question you have to answer is, how are you pushing epsilon into the bulk? That depends on some gauge choice. Anyway, you have to put in some extra information and you push it in somehow, and then you can ask that question. But in this case, because it's an abelian gauge group, yeah, it doesn't matter. Okay.
I put it in the same way I just define fall-off conditions, but these are gauge gauge.
Fall-off conditions are also defined by first choosing a gauge. So again, yes.
Yeah, so
some
you
gauge.
use F for that. So
Yeah,
it
right.
won't make any sense.
Yeah. Okay. Let me just make a few more comments, so I'll be done with QED. Okay, so we've now seen that these charges, well, they exist. They give you non-trivial information about the S matrix in the form of soft theorems. So what else do these charges tell us? Let me, for instance, just write down what was the charge again? Q epsilon plus is integral epsilon dA FUA, or let me write this as dA epsilon FUA plus integral epsilon JU to 0. Okay, so maybe the first interesting question to ask would be, what is Q epsilon acting on the vacuum? And by this vacuum, I just mean the usual perturbative vacuum that is just assumed in quantum field theory. So clearly this is not 0, because this is, so this acting on the vacuum is 0, because this is just a, it generates gauge transformations on the vacuum. So this is just 0. Whereas this guy is not 0, because it's linear in the fields, and it adds a soft photon. Right? So this is a new state. And because this is a gauge transformation, this charge commutes with a Hamiltonian. So this state also has 0 energy. So it's also a vacuum state. So this immediately tells us that the vacuum is not unique, which is kind of assumed in quantum field theory, but it's certainly not true the moment you have gauge fields. So this tells you that if I do pick up certain vacuum, then all the gauge transformations are spontaneously broken, because you're shifted to a different vacuum. The only set of gauge transformations which are not spontaneously broken are the ones for which Q soft is 0, which is only for which dA epsilon is 0, which means epsilon is a constant. So these are just the global gauge, global U1 transformations, which of course you're familiar with. So those ones are not spontaneously broken. But these other ones, they exist, but they're spontaneously broken in any vacuum. In particular, this tells us that if I start with any vacuum, I can act with an arbitrary epsilon, so there's really a function's worth of vacua. So in a generic quantum field theory, you have this vacuum which is parameterized by a whole function. And again, because this is an abelian group, this is a nice sort of group, so then this is just F plus epsilon. So acting with some arbitrary epsilon just shifts the vacuum in this very simple way. Okay, so that's the first comment, that you no longer have a unique vacuum. So you have to worry about these vacuum shifts. So what would that mean? So let me now be a little bit more careful, and let me define the following operator. Just NA is just the U integral of this 0 mode. So it's the guy that generates the soft theorem, that inserts a soft photon. Okay. Suppose let's consider an S matrix in which I have an in state, and now you have to be more careful. So I have to also tell you what vacuum I'm building the Fock space on, right? You have to start give me a vacuum, and then you can do whatever Fock space you can build on that. So this in describes all the Fock space business, and there's a certain vacuum. So let me choose a vacuum which is an eigenstate of this operator n. N commutes with itself. That's because it's a photon, so photons. So this would be more complicated in non-abelian gauge theory, but so I can choose the vacua to have this. So let me choose this guy. And a generic out state, but with a different vacuum, different out vacuum. Okay, this is really the most generic S matrix you can compute in QED. Yeah, but as I said, this 0 mode satisfies NZ bar minus del Z bar NZ equal to 0 in the absence of magnetic charges. So I can write one or the other, it doesn't matter. In fact, maybe the correct thing to do is to say NZ is del Zn. That's what that means. I'm sitting on a sphere, so I can just solve it with that. That's not necessary though here.
He was asking that the n's are functions, not numbers.
Yes. All of these are functions. The vacua are labeled by functions. Yes. Sorry, yes. So NZ is a function which labels the vacuum, and then the in just labels the Fock space that I'm building on top of it. Yeah, so here I'm choosing the vacuum, the basis such that it is the eigenvalue of this operator n. Yeah. Okay. So the ward identity still holds. That's the power of spontaneously broken symmetries, because even though the symmetries are broken, ward identities and all still hold, and you can still obtain non-trivial information. So if I were to work in this vacuum system, so note that this is not the same vacuum that is usually used in perturbative QED, because NZ acting on the usual vacuum does not give you back the same state. It gives you this state with an additional soft photon when we typically do quantum field theory. So the ward identity for this sort of in and out state will be slightly different. So what does it look like? It basically, so everything else follows through in exactly the same way. So this statement is still true. But now Q epsilon acting on the out state simply gives you NZ, because it's an eigenstate. And the positive one gives you this one, which is an eigenstate. The hard guys just don't care about the vacuum. They only act on the Fock space. So the right-hand side basically stays the same. And then let me again go ahead and choose epsilon to be 1 over z minus w. So the full outcome of this entire process is the following statement. So the ward identity implies nz out minus nz in minus omega z for this S matrix is 0, where omega z is just a sum over k qk z minus zk. This is this right-hand side. The point about this statement is that if, as it is usually done in QFT, I assume that the in and out vacuum is the same, then nz out is equal to nz in. This is a non-negative number. Then the S matrix is necessarily 0. This is exactly what we see with infrared divergences. That assumption gives us, we make that assumption all the time, and we do the calculations, and the S matrix turns out to be 0. That's not surprising. This is the reason. So the correct thing to do is to account for the fact that you have these soft radiation, and to account for the fact that the in and out vacuum is not the same, but is related. So you clearly need, in order to have a non-zero S matrix, this relation to hold, that nz out must be equal to nz in plus omega z. And yes, as I said, the precise vacuum you're in is not measurable. The change in the vacuum is the only thing that's measurable. Yeah, so it's very precise. It kind of depends on the set of massive particles that you're scattering, right? Because omega z depends. So actually, it doesn't matter what nz in is. You can choose nz in.
Yes. Difference can be 4. What is the?
No, difference is fixed. It's exactly this. As a function, it's fixed. So this is omega z as a function of z on the sphere, and it's fixed in terms of zk and qk, which are the set of all particles that's coming in. So you have to do this to get a non-zero S matrix. And in fact, there was a paper which worked this out in detail and basically showed that if you do this, you get finite S matrices. And in a slightly different formalism, not like this, that's exactly what Fadhib and Kulish did. So Fadhib and Kulish actually showed that there exist states where you take charged particles and surround them with a cloud of soft photons in a particular way. And if I do it in the way that they describe, you can get infrared finite S matrices. But what they were doing is just this. Is just making sure that their clouds satisfy all of these properties. But a cloud of soft photon, which is kind of difficult to describe in their language, is just a choice of vacuum in this language. So it's slightly easier to at least describe physically, what's going on.
But if having charged particles, then it follows some reasonable accelerated trajectory. So moving the accelerates for a while, stops and moves again. And I compute the electromagnetic field. And then try to decompose that into photon number.
Yeah.
Would it be infinity?
Yes. Yeah. Well, the soft mode don't have a well-defined notion of photon number.
But if you take the integrals
Yeah.
as you go from 2 omega.
Yeah.
and omega,
Yes.
limit would diverge.
That would diverge.
So this is what you're saying that in this, maybe one way of saying what you're saying is that the idea that you're working in a Fock space never worked
Yeah. Yes.
because Fock space is finite.
No, from zero energy.
Is that right? It's
So,
not that you get some integral which is divergent. Sounds odd, right? I mean, usually divergent.
well, yeah, well, yes, when I do the usual Fox-based thing, I think, yeah, it is coming from, yeah, that is true. It's coming from, even if I give an epsilon cutoff, yeah, exactly, it grows as 1 over epsilon.
So you haven't really solved the problem.
Yeah,
How-
I
how
suppose
can
that's
you
true.
use the infrared divergences by just doing this? I mean, what about things coming not from the exactly zero sector but anything?
This is the problem you also mentioned last time, not able to being distinguished.
But you're claiming a very interesting result. You're saying that
Yeah.
just this fix in the zero energy sector gives you infrared finite S matrices. You would have thought that you need to fix more than just zero energy into it. Where I was,
Yeah, I think the idea is just,
or this fix also fixes.
yeah, I think it certainly also fixes that. I'm trying to imagine how it fixes that. Right, see, there's also this one problem that, in the usual Fox-based thing, you actually never have strictly zero energy modes. You only have infinitesimally low energy modes. And I think I think what I'm saying here, I think what's going on here is that those infinitesimally low energy modes are being recast as exactly zero energy modes and then described by shifts in vacuum. So one thing I didn't note is that you usually just do a mode expansion of your field. But that's actually not, you can't do mode expansions for your fields because you'll just see that a generic field does not allow for mode expansions because the moment you do a mode expansion, you're already assuming some sort of boundary falloffs. And in particular, you'll see that these strictly zero energy modes, this n. So let me just quickly mention a classical analysis. If I want to include this zero energy mode n in my phase space, then I also need to include its symplectic partner. But its symplectic partner is not part of the mode expansion. It's actually a separate mode altogether that you have to introduce in addition to this, which is, we have called it C, but it's basically the sum. So n, this is a U integral, so this is just AA at scribe plus plus minus AA at scribe plus minus. That's NA. And this is the new mode, which is the symplectic partner of n, which you have to introduce, which is plus AA. And you'll see that any field that has a mode expansion, this mode is just set to 0. You can, again, do the saddle point approximation and the thing, and this is just 0. So clearly, this is not a mode that's even considered in standard quantum field theory because you just do a mode expansion without thinking. So this extra mode needs to be introduced, otherwise you don't have a well-defined problem. And I think that has to do with these things. So all these infinitesimally small modes are somehow associated to this C. Yeah.
This is raising and lowering operator.
Essentially, one of them is, yeah.
And one kills the vacuum.
So C kills the standard QFT vacuum because it's 0. You do a mode expansion. But delta C under gauge transformations is del A epsilon. So clearly it's not preserved by these large gauge transformations. So if I want to include large gauge transformations in my phase space, then I need to allow for C being non-zero.
What is the statement of unitarity? Is there you're claiming there's some well-defined S matrix?
We haven't tested unitarity. But yes, this.
Meaning, for instance, when you decompose in the middle, with which vacuum are you supposed to? Or are you supposed to sum over them all?
I think, yeah, you should sum over them all. You should sum over them all.
That summation. I mean, if you've got a nice finite S matrix,
Yeah.
one of the great things about S matrix is the unitarity.
Yes, yes.
What do fuzzy coolest make of?
No. No. That's a good question. We have not analyzed at all, or
The
even.
great thing about unitarity is it's precise in things.
Yeah.
Another statement which reminds me of is this Villa approximation.
connected like here, but rather a vacuum multiplier.
Yeah,
And
this
the other states are also.
this is slightly different from that because in usual spontaneous symmetry breaking, in any spontaneous symmetry breaking, there's no physical process that actually allows you to change the vacuum. No finite energy process will change the vacuum. Right. I mean, just for instance, just the Higgs mechanism. There's a bunch of vacua, but once you've chosen a vacuum, no finite energy process will ever move you away from that vacuum. Yes. But here any S matrix changes the vacuum. So you no longer have like these super selection sectors or anything like this.
Or CFT3 will be the exit. This cell does not
That's
have
true.
these two dimensions. So for instance, the Ramsey deformations
Yes.
or the Krasnow model that Amit is talking about, there you can think of all the downhills as large switching occlusions on a particular vacuum state, which is like pure radius free and in general Robert length,
Mm-hmm.
and they all carry these non-zero charges. So except that these modes that you were saying that some things carry absolutely zero energy.
Yeah.
That is surprising me because in downhill there is no such thing. And all the charges, they all create. I mean, every downhill deformation carries some energy of that.
Yeah. Yeah.
There is a non-specific, zero energy vacuum.
I think that just has to do with the fact that ADS3 just has a quadratic potential, right? I mean that even a massless state, kind of even what you would think as a massless state is sitting inside a quadratic potential in ADS. So it has some non-zero.
Magnetic energy. Yes. Yes. So that's like this number operator. But here in standard energy,
N0 equal to 0
that's like the energy.
there's only one. I thought there's just a fraction of the
But there is a sense in which the action of negatively moded Virasoro on the vacuum also vacuum.
But they have different L0.
Yeah.
And so in what sense are they vacuum?
In the sense that you are creating them from the vacuum by acting symmetry.
I see.
But they don't commute. The symmetry generators, they don't commute with
L0.
Yeah.
Yes.
Yeah. But L0 is, I think, is basically number operator.
So here, how does it work? How does the algebra work out? I mean, in the sense that there's an energy operator. So this NA guys.
Well, the energy operator in this case is just the Hamiltonian, so
Yes.
which has nothing to do with these, which n doesn't appear in that because it's a zero mode. So the Hamiltonian only contains all the other non-zero modes, and n commutes with all of them. Well, you wouldn't expect it to have anything actually.
Also, this
Yeah.
cloud of photons sounds like you're taking descendants into account with respect to this.
Yeah, yeah. I think that's right.
This is like what I said.
Yeah.
Towards the where Virasoro's found out something is happening. Even a four dimension, Virasoro's found out something.
Yeah. Yeah.
So there, where I guess that you're not talking about nevertheless, one would essentially consider Virasoro different.
Right, right, right. I think that's. Okay. So, okay, let me just make a few quick comments. Some more comments about, like, some generalizations. I said here I mentioned the simplest, literally the simplest theory for our purposes, massless QED with all massless particles, with no with no magnetic charges. So already I've explained what to do if there are magnetic charges. Then yes,
The data for an estimation
yeah.
would remain what just the data of the hardware.
No, no, no. So now the new data is N and C. You need to prescribe both of those things.
But the computation laws tell you that you know what the hard photons are doing, you know what the changes in it.
You know the.
You know N out minus N in.
Well, yeah. So if I tell you, yes, C is the new data.
But it doesn't appear in the S matrix, right? The S matrix is a function of, let's say, some momentum polarization. I mean, in normal QED, when I compute the data, an S matrix, I give you a function of momentum and momentum polarization.
Yeah.
I was just trying to understand whether you're saying that I should add new labels to that. And you're probably saying no.
Huh?
You're probably saying no.
Yes, yes, yes. Not to that, but well, you have to add new labels in the sense of what is the in vacuum and the out vacuum.
But there's no new data. I mean, if I tell you what it is for one in vacuum, it's
Y-
only
yes.
for a particular out vacuum.
Yes, yes,
And I presume that if I shift N in and N out equally,
yes.
nothing changes.
Exactly. Yeah. Okay. Yes. Yeah. Absolutely right.
So the non-trivial data continues to be in momentum and polarizations of
Yes.
non-zero.
Yes. Correct.
So once again, there should be a unitarity equation in terms of the usual data.
Correct. Correct. I think that's right.
Norms of all these vacuums?
That's norms of all these states are zero.
Are zero?
Yeah. In the natural norm,
Vacuum is not more like
no, even the vacuum is no longer norm 1. You should really be careful. The vacuum is now, because it's labeled by a function. It's like this. It's a functional derivative. And so the finite S matrix that you're computing is, you have to divide out by this norm. And that's the finite number that you compute. Yeah. But Shiraz asked this question. I don't think it's been, like, what is the, I mean, you would have to know that exactly to understand the measure also on this. I don't think people have thought much about this.
also this algebra symmetry, is that making sense?
Not for QED. So the algebra of the commutator of the charges is associated to commutator of soft limits. So just take two soft limits. You take one photon soft and then the next one. So it has to be one after the other. And then you do it in the reverse order, and then you take a difference. So that's the commutator of soft limits. You can basically show the commutator of charges. The Ward identity for commutator of charges is equal to the commutator of the soft theorems, and the central extensions would be related to possible quantum corrections to soft theorems. And QED soft theorems are tree level exact. So strictly speaking, everything I've done here is semi-classical. So it's right to ask whether there are any sort of loop corrections. But in non-abelian gauge series, there are one loop corrections, and it's a one loop exact. So you might expect that there might be some corrections there, but people have not again.
So say that again, non-abelian gauge series, what?
In non-abelian gauge series, the soft theorem is not. So I've written down what the soft theorem is. It gets a one loop correction.
I would have thought a non-abelian gauge series whole structure would be totally void because of confinement.
Yes, yes, no, well, yes, but I'm assuming that there are massless particles, massless gauge fields, so you really have to consider a non-abelian gauge theory with no confinement. That's otherwise
Okay.
this entire thing doesn't apply.
Again, I would have thought that the structure would have been totally modeled in n equals 4 angles because it's conformed.
Yes,
You're saying there's some one loop exactness in n equals 4 angles?
that's what yes, I don't have an understanding of that. That's what computations have shown. But what I was really saying is just consider non-abelian gauge theories and put in some arbitrarily large amount of matter field so that there's no confinement and it's not informal. Yeah, yeah. I mean, if there are no massless gauge fields going through Scribe plus, then then there's nothing to say here.
Okay, yeah, good. So there's nothing to say. So the soft theorem should be something same, replaced by some confinement there.
Yeah.
When something's IR3, it's plausible that classical analysis gives you, or some fault correction gives you.
Yeah.
But there is the edge between them,
Yes.
which is conformal,
Yes.
which I somehow strongly doubt that anything classically takes place.
Yeah. Yes. I agree.
How do you construct?
Or just put in like 10 matter fields, like in the beta function just becomes. Yeah. So that's the formula. Those are the kind of theories to which this would apply. So this has nothing to say about confinement or anything. Okay.
Fahad, I'm going to soon
Yes. Yes.
head off to something.
Okay.
I'm sorry to.
Yeah. No,
You
that's
should
fine.
continue this.
No. So we're basically, I've said everything I had to say about QED. And the point is that everything else beyond this goes through in exactly the same way for gravity as well as for gravity as well as non-abelian gauge theories.
We haven't yet heard. I mean, two legs of this triangle have come into play. This memory has not yet.
Oh, I wasn't planning to talk about it, but the memory. Let me at least tell you what the memory effect here is in this case. You consider two charged particles that are sitting somewhere. And an electromagnetic field passes through them. So you have to take two charged particles and you have to make sure that their phases are the same. So you do some Aronoff bomb. So here, because I'm doing gauge transformations, the memory effect is.
The degeneracy of vacuum inverse, is that what the memory is going to do?
Yes, it's going to explain it. Yeah, yes. So you take two electrons, and you ensure that their wave functions have the same phase, right? Now some electromagnetic field passes through, and you wait for a long time after it's completely passed through. And the claim is that the relative phase would have changed, and the change in the phase is this large gauge transformation. That's it.
You could have waves without a soft.
No.
I mean, because there's no interaction now it's not necessary.
No, there's a constraint that tells you there's this constraint. There's the Maxwell constraint that tells you that any time I have any sort of radiation coming through, it has to satisfy the Maxwell constraint, which means that the soft part must always be there, even if it's not interacting. I mean, even for GR, the exactly zero modes are not interacting with the energetic modes, so that's not the problem. But they need to be there because of these Maxwell constraints, and in GR,
No, I'm not understanding this. I mean, in pure Maxwell theory, without any charged particles, plane waves of any frequency are just silly.
Yes.
So I can have a plane wave with no zero component, that's just exactly silly. Jackson tells me that, I don't believe that.
Yes, that's of course true.
It's also true
let me
that
see.
once you have charged particles coming,
Yes.
there would be.
Yeah.
You need some element of that.
Yeah. Okay. I think that's right.
So these charged particles that you just had were four particles.
Yeah. So what you said was correct. Yeah, that's exactly right. That's exactly right. Okay, so without going into too many details, let me sketch out what happens for super translations, and I think I'll talk about super rotations tomorrow. Maybe that's also more interesting because that's where the stress tensor comes in. So quickly, let me tell you what happens for GR. So in GR, you have the metric, and I'm going to think about the. I'm looking at, I'm looking at perturbations here. I'm looking at Christodoulou-Kleinemann spacetimes, which are very close to flat spacetime. So I'm looking at metrics which are flat. So this is very far away from everything. So near square plus. So they're mostly flat. And then there are corrections, subleading corrections. So for instance, one correction you're familiar with probably is this guy. So this is just the Schwarzschild black hole. This is just the mass of the. But the more interesting one are these R CZZ plus R CZ bar Z bar. Probably not surprising is that these are the transverse modes, so these are the two gravitational polarizations. In higher dimensions, you just get something like CAB dx dxp, and this is a traceless symmetric tensor. So these are the, and A, B are the d minus 2 dimensional indices. So these are the polarizations of the graviton. And then there are others which I don't care about. There's a matching condition for MB.
CZZ and CZZ are going to be related to what people call the news.
The news is the derivative of that. As expected, because the gravitation waves really are, the fluctuations, so it's captured by the news. And this is going to be the point, that if I'm sitting in pure vacuum, no gravitational waves, no nothing, n is 0, but that doesn't mean C is 0. C can have a 0 mode component, and those are going to be the soft modes. So there's a matching condition for MB, and I'm actually, maybe I should probably say it tomorrow, but there's this other mode which is NZ du dz. This n is not the same as that, but now I'm doing gravitation. This NZ is the angular momentum tensor, so it computes angular momentum in GR. This is going to be associated to superrotations. So that's the matching condition, antipodally mapped. So which means you just multiply by your favorite function and then integrate. Right? Now some very simple things you can immediately see. If f is 1, this is the integral of this, the 1 over r component of GUU, that's the total energy. So this is clearly measuring some sort of local energy at every point. And I'm going to do the same thing, write it as a scribe plus integral, and you have the Hamiltonian constraint equation for GR, which, what was it? Here, which is 1 over 4 dA dB NAB. This is the news, minus TUU. This TUU is the stress tensor that includes the gravitation plus matter. So for instance, it kind of includes a term that looks like NAB squared plus TUU matter 2. So the 1 over r squared component of the stress tensor, matter stress tensor. But it also includes the gravitation, the component of gravitation. Right? So again, as you see, the structure is similar. There's a linear piece, right? Which is again, there's a linear piece integrated over u in exactly the same way. So it's a u derivative, n is the news. It's the u derivative of the gravitational fluctuation integrated over all of u. And so exactly like it works out here, that's going to give you a soft graviton. And then on this side, you get the hard part, which now also includes a gravitational self-interaction. So gravity interacts with itself, and then some matter interaction. And so again, you do the exact same thing that we have done so far. You work out the Ward identity. That's going to be the soft graviton theorem. And again, the same argument holds here. There is a, in this case, the Christodoulou-Kleinemann constraint, which is dz squared c z bar, which is the analog of this constraint. the GR analog of this no magnetic charges constraint, there's a no magnetic Weil tensor. There's a magnetic component part of the Weil tensor, which you set to 0. So there's this constraint, which again tells you that soft gravitons, you don't have two different polarizations. You just have one single polarization for a soft graviton, which is now coming from this CK constraint. So that's the story for super translations. Again, infinite number of vacua and all of the things that I've said follows through in exactly the same way. Super rotations also really follows through in exactly the same way, but I think I'll talk about it tomorrow because it contains a stress tensor and there are some other interesting things to also say. I'll stop here. Thank you.